Welcome to Hot Chips 29. Session 1, GPU and Gaming.
So welcome to Hot Chips. My name is Jose Renau. I'm the Hot Chips 29th General Chair. Next. Next. So this year we have a great attendance. So what I'm showing here in a plot, I'm a computer architect. I cannot avoid to do plots. So what I have here on the plot is the registration through many years. Those are the thin lines. And the green thick line is the registration as is happening as we get closer and closer to the conference. As usual, there is exponential increase close to the deadline. And what we have is around 10% more than any previous years. So we are growing, and it's a very thriving community. So thank you for registering and coming. So we have a great attendance. We also have a very strong technical program. In fact, we have around 20% more submissions than last year. So you will see that there are what I think very interesting papers. And one thing that I have to thank is we have a very broad sponsor support. I don't know if you have noticed, but this conference is relatively low registration cost. And one of the things we have to thank is the sponsors, because they sponsor the conference, and we can give access to a lot of people. So there are many levels of sponsors for bigger companies, smaller companies, and those are the sponsors for this year, like Cisco, Flex Logic, and Intel are gold platinum sponsors. And then in the gold sponsors, we have also a lot of companies: Ciba, Nvidia, Huawei, ARM, AMD, Acronix, DeFi, and Qualcomm. And then there are other levels of sponsors, from small companies to others. Not so small. So one thing you have to make sure is, like, as you register, try to make sure to get the USB stick, get the bag. And this year we have also a bottle, so you can have your coffee, your water, whatever you prefer there. Remember to get them. One thing that I have to say is that we were not able to get there's a missing gift. So we thought we could bring glasses for the Eclipse, but they got stuck at customs. And we are not able to provide them. So sorry for that. If you want some glasses on Tuesday, maybe we'll have them on Tuesday, but until you can keep them until, I think the next one is 2014. I don't know what we are going to do with them. One thing that, I'm a professor at University of California, so I volunteer in committees. I've never seen an organizing committee put in so much effort. So one of the reasons why the cost is so low, there is a lot of dedication from the organizing committee. So I want to thank them for all the effort that they are doing. Thanks to them, we can have this conference. Now, obviously, there is also the steering committee, which is very important to maintain the traditions on the conference and keep going through years. And we have the program committee with the chairs this year with Fred Weber and Mike Taylor. They have a strong committee, as we tend to have in Hot Chips, and they have been able to pull a very interesting program. So for Monday, what is the schedule that we have? After I finish, and it should be soon, we have the GPU and gaming. But because we have the solar eclipse, we are going to have a break. Now, We don't have the glasses, so I don't know how you're going to see the solar eclipse. We'll try to project something here, maybe through your, I'm going to use my phone to look at it. So if it gets burned, the phone is OK. But then we'll continue with the GPU and gaming. We'll have IoT, and as usual in hot chips, we're going to have many breaks. So you can mingle and talk with other people. We'll have lunch from 12:30 to 1:45. And then we'll have a keynote from a previous DARPA manager. So we're going to get some insights in direct human and machine interface. Then we'll go to automotive. In our community, we know that it's an important topic. I don't have to go over that. And then another break, and then processor, and then another break. Now, Tuesday, we are starting a little bit earlier. Because we have so many papers, we have to push a little bit the limits. I commute from Santa Cruz, so it's going to be tough for me to come here. But notice that we start earlier than today for tomorrow. So the breakfast, 7:15 to 8:15, but then we have the FPGA talk from 8:15 to 10:15. Break, neural net, another keynote in advances in AI. And then we'll have continuation neural nets, some architecture, and then the final talks is some of the server chips, as we tend to do, and some closing remarks. So one thing, we strive to try to improve the conference as much as we can, and we want your feedback, so you have some papers to provide feedback, but feel free to talk to anyone who has like the white shirts and to provide some feedback on whatever you want. And we have an evaluation form at the end. Now, one thing that I noticed this morning is that some people were parking in some areas that it marks stuff on the floor. And you can get a ticket if you park there. There's also some areas that is with meter. You shouldn't park there. So remember, you have to show a printed version of what we have on top right, that the hot chips, that everybody has it, I think. The main issue is make sure that you park where it says park here. That is the area that is on the right. There are some very few parkings close to the yellow area. Do I have a laser pointer here? There are some parkings around here, but very few that they are not marked with stuff. But you have to be careful on that area not to park. As long as after the break or during the solar eclipse, you were there, maybe you want to move the car. Now, one thing that we have is that we have an internal website, and we are uploading the slides, and there might be some last-minute edits from the speakers. So we're uploading the slides on this website. So if you want to connect, this website has the latest version. You can get them. For example, yesterday, there was the Nvidia slides. Some of the slides were not on the USB drive because they got at the last moment. So you go to this website, you can connect, and then you'll be able to get it. I'm not mentioning how to connect through hot chips. So the Wi-Fi just go hot chips, and the password is hot chips, and you should be able to connect, and then you can go to this IP address. So I'll keep the slide a second so you can copy the IP address or take a photo. This is not the full website like what you see outside. It's just the talk slides link. So that's everything I have to do. Just an introduction, and thank you for the sponsors. Thank you for coming to the conference, and enjoy the conference. And we'll start soon. Thanks.
Can we get the, oh, very good. Good morning, everyone. Again, I'd like to introduce the GPU and gaming session. Very excited about this session. We have 3 GPUs. Actually, it's one iGPU inside the Xbox SoC, and we have 2 discrete GPUs. The first talk up will be John Sell from Microsoft. He's a distinguished engineer at Microsoft. He's been the architect of the original Xbox chip, and now he's back here 4 years later to present the Xbox X Scorpio. He's been with Microsoft for 12 years. Previously, he was at AMD, hence also the good collaboration between Microsoft and AMD on the Scorpio chip. Prior to that, he was at 3DO, and he was also at Apple before that. He holds an MS in EECS from the University of Berkeley, and here is John to give you the introduction of the Xbox X Scorpio chip.
Great, thank you. Let's see if everything works here. The Scorpio engine is the SoC inside the new Xbox One X console. Initially, the name of the project was Scorpio, the internal name. Microsoft decided to introduce that name publicly, and now that the system has a name, the Xbox One X, the SoC inside's been christened Scorpio, the Scorpio engine officially. So let's see here. So here's just a straight-on shot of the chip module. It's like the original chip inside the first Xbox One. It's one of the largest in 2017 mass production consumer chips. It has approximately 7 billion transistors. It's a 359 square millimeter TSMC 16 nanometer FinFET plus process technology. One of the most important goal of the whole project was to provide a system that would have true 4K gaming performance. And that starts with GPU performance, but it really requires the rest of the system on a chip to match. Memory, fabric, video, encoding, decoding, display, and of course audio. And I also wanted to, before I move on to the next slide, wanted to say I'm very pleased to say that that Scorpio's been the result of a very successful collaboration with AMD. So let's take a look at what's physically inside. So this is a die photo, probably like after the first with the first metal layer. The large yellowish areas that you see in the kind of to the, there we go. I can make the mouse behave here. Maybe I'll just point at it. But anyway, the large yellowish areas and the area between them that are taking up most of the chip, sort of in the central and to the left side. Those are, that's the GPU. The majority of the GPU is divided into 4 shader arrays. Each of them contain 11 compute units. 10 are active, 1's a spare. So there's a total of 40 compute units, and then 4 spares for reliability and yield. The kind of dark green areas with a little bit of yellow cache arrays are on the right side of the chip are the 2 clusters, each of 4 CPU cores. And then kind of going across the top of the chip, the bottom of the chip, and the right side are the 12 GDR5 memory controllers. This drawing is, I know it's going to be hard to see except near the front of the room. I kind of consciously decided to make it this detailed because I wanted to be able to present to you a bit more detail than you usually get in this kind of presentation. As Ralph said at the introduction, I guess you can download this presentation either from the local website, and it's either if it isn't there, it will be within a few minutes. That's probably especially for you in the back, the best way to see this drawing. But in the meantime, want to describe a few things about it. I hope one thing that it kind of gives you the impression of is that there's an awful lot of connectivity in this design. And it basically takes a lot of connectivity to move 326 gigabytes per second of memory bandwidth around. The system comes with, as I mentioned before, 12 channels of GDDR5 memory. It operates at 6.8 gigahertz data rate. The system that that will be available includes a total of 12 gigabytes of main memory. The development systems have twice as much, 24 gigabytes. The GPU, which is the kind of bright Xbox green thing in the middle left of the drawing, can use the full memory bandwidth. It's connected through 12 256-bit wide pairs of buses going to each of the memory channels. They are, we've actually ran tests where we're able to use about 285 gigabytes of the peak 326 from the GPU. A typical game is not going to use that much on average, of course. And the peak that would be available is in the order of 300 gigabytes after refresh. A portion of that bandwidth can be CPU cache coherent. The sort of vertical two pairs of channels that are just in the center of the diagram a little bit to the right side, they're running vertically. That is the path that coherent traffic takes. We specify, as do all the Xbox One systems, CPU cache coherency is part of the page tables of the GPU and actually all of the other devices, I/O, audio, and the devices or the requester itself can also override what the page table says. But the decision about whether a given 4K, 2 megabyte, 1 gigabyte page is CPU cache coherent is driven by the information attributes in the page tables. I'm going to go into a little bit of detail about the CPU and GPU and other units on following slides, but just one point to make while I'm on this slide. The kind of area about in the center of the slide, let me try just maybe see if I can point that out here. This area here is the main, not the only, but is the primary path from the GPU to memory. The GPU has 8 render blocks and 8 256 kilobyte L2 caches. Are these boxes here. They're connected to the interfaces to the memory system through an even more complicated or more, I guess, impressive, I would say, interconnect in order to be able to utilize all of the memory bandwidth. There are 64 outbound and 40 return 256-bit data paths. For the drawing, each of those connections is indicated by one of those little green dots, but that essentially is a 256-bit data path. But that is part of really delivering the performance that the chip is capable of. So just to say a bit more about the GPU, I guess the sort of top line is it has its raw arithmetic performance, or 32-bit single precision floating point performance, to be more specific, is just a hair over 6 teraflops. We kind of wanted to hit that number, and hence the GPU operating frequency of 1.172 gigahertz. Each of the 40 compute units can perform at a peak rate of 128 floating point operations per second. There are a lot of other features, some of which I've listed on the slide, that contribute to the performance of the GPU besides just its raw arithmetic capability. Probably one of the most important ones is the work that we've done to optimize the GPU control processor firmware and some special hardware attributes to really integrate support of our graphics API, which is DirectX. Well, some applications use pretty much vanilla DirectX 12, and there are enhanced versions for games to use that allow them to get closer to the metal, so to speak. That does two things. It lets an application extract more performance out of the GPU, but it also reduces the workload of the CPU to set up the work that the GPU is going to perform. Some of the other features that are really important to the performance and new features that we're first introducing into Xbox with Scorpio are listed on the slide. Make one comment about the bottom one, though. The Scorpio, the Xbox One X, is 100% compatible with the Xbox One S and the Xbox One games that have come before. And it also has compatibility with the older Xbox 360, similar to the current Xbox One S. Just to make a few comments about the CPU. CPU is derived from the CPU that we used in the Xbox One S. It's 8 x86 architecture cores. In the case of Scorpio, it's operating 31% faster than the Xbox One S, and it's actually built in the same 16-nanometer FinFET technology. So we did extensive retiming of the CPU, and to actually make that extra performance available or realized in a typical application, we done several other things, many of which I've listed on the slide. Most of them are oriented around getting lower memory latency or lower average latency. We actually literally reduced the latency to memory by up to 20%. The amount depends to some extent on what other activity is going on. So if there's relatively little other activity interfering, then it would be at the high end of that number. We've also greatly enlarged the TLBs in the CPU, and we added a redesigned and larger new page descriptor cache. What this does is it's a little like a TLB, but also a little bit different. It caches information about nested page translations. All of the Xbox Ones use are hypervisor-based systems. So they're doing the hypervisor is controlling the physical location of pages. Page translation consists of going from a guest virtual address to a guest physical address, and then the guest physical addresses have to be translated into the actual physical address. Without the assistance of the page descriptor cache, this would, in the basic 4K page case, involve about 4 times as many memory accesses. The page descriptor cache lets us eliminate almost all of that extra workload in typical situations. The 4.3% performance increase that's cited is with spec 2006 benchmarks. seem to have gotten stuck here. See if I can go the other direction. Nope. Not going anywhere. Nope. Seem to have died. Let me just get it. Seem to have a freeze on our display here. No, just not getting it. There we go. Guess the computer wanted to talk about the CPU a little bit longer. So throughout to make Scorpio be a true 4K experience, you have to, of course, worry about more than just the GPU and the CPU. So the audio and video components have all been substantially enhanced. We use video decoding for cutscenes in games, and of course for multimedia like 4K Ultra UHD Blu-ray, and so it can decode a genuine 4K P60 hertz, several different formats, including 10-bit high dynamic range. Similarly, video encoding for game replay, for streaming, which is becoming very popular for other people to watch what you're doing. The display has been enhanced also to support, all of the Xbox Ones have allowed blending of multiple surfaces and resizing them. Those in Scorpio can be as many as 64-bit pixels, 4K resolution, or larger in some cases actually, to be resized downward. We support several other new features, and most important, 10-bit HDR, high dynamic range components. The audio is very similar to the Xbox One S. It runs a little faster. We have several new firmware features that are being added. One example is a new spatial surround sound capability. Many of those are also going to become available for the Xbox One S because other than a slight speed increase, the 8 custom audio processors are very similar. So let me show just briefly here a quick look at what the system looks like. The SoC that I've been focusing on, the memory system, the south bridge. We have a single chip that serves as a south bridge, provides all the clocks in the system and other basic power sequencing, other system control functions. Xbox One X comes with a 1 terabyte hard disk and comes with a 4K UHD Blu-ray player and various range of USB video in and out, IR and other interfaces that you see. Great, thank you. And I guess we have time for a few questions. And also afterwards, if someone would like to, I brought a few samples.
So we have time. We have time for a few questions. If you come up to the mics on either side of the seating, please state your name and affiliation.
Hi, Charlie Demergent, Semi-Accurate. On the last Xbox, you seem to go memory bandwidth light with large caches. On this one, you seem to have swung the pendulum quite distinctly the other way. But you didn't mention any of the caches or on-die caches. Are they there? Are they enhanced? And why the whole paradigm shift?
So there is nothing like the 32 megabyte embedded SRAM that I think you're referring to. That is gone. There are obviously the CPU retains the same essentially the same caches as it had. The GPU has caches as well, and they're increased, but they're not the embedded memory. You're exactly right. We've looked at what's available in technology. We've looked at what we could accomplish. Frankly, we're a little nervous at building a consumer product that's going to move data at 6.8 gigahertz when we started. But that's been one of the most successful parts of the design. It's a lot simpler for our developers to have a unified 12 gigabyte, all same full performance level memory system.
Given that the cache was used for more than just a cache, there were several system functions on that. Did that cause any problems with?
No, so the 32 megabyte SRAM that the Xbox One and One S have is, for compatibility, it's emulated as a little small part of the memory system. The bandwidth of the GDR5 memory system we have it's about 3 times the typical bandwidth that could be used out of that onboard memory. It's about 1.5 times the absolute theoretical peak of that older onboard memory. So it has more latency, of course, but that onboard memory was used pretty much exclusively by the GPU, and the GPU is designed to handle the longer latency. So even on the older systems, the GPU thought of that onboard memory as being another part of its DRAM memory space, if you will, even though it was actually on board. So no, we haven't found any performance issues by having it all be in main memory. And in fact, just the power of the new system, it's really quite easy for it to in most cases improve the performance of older games when they're run on Scorpio. Anyone? Take one from this side. Go ahead.
Shaigalon, Cavium. You mentioned the Pages crypto cache. You were seeing 4.5% on spec. Can you clarify, was the spec running on the VM or?
Yes, it was. I mean, this essentially that gives us back. I could say it. Essentially, it gives us back the performance that would have been lost.
Got it. Thanks. Michael, during Tectus, you describe your overall pixel as 64 bits, and then you describe your HDDR, dynamic range rather, HDR, as 10 bits. Can you say a little bit more about how?
Well, we're supporting many different formats. The 64-bit that I was referring to is different applications who use different things for different purposes. But if an application has prepared one or more of its surfaces as typically FP16, so for 16-bit floating point components, then we can handle those. We can, as the slide mentioned, we also can handle them with pre-multiplied alpha, which means we can remove it and blend and put it back, put the alpha back in, for example. Those are some of the enhancements that Scorpio includes. In terms of the 10-bit HDR that I referred to, that could also be handled as inputs, but that's probably most relevant as final output formats. So I'm kind of mixing this. There are many different formats at different stages of the rendering process, and sort of mixing them together a little bit.
Thank you.
David Cantor. So quick question for you on sort of power management. Since you're designing the whole SoC, including all functionalities, did that give you greater opportunities for optimizing system-level power management?
No, absolutely it does. And we've always, from the beginning of from the first Xbox 360 through the Xbox One and through Scorpio, we have done that. All we do so to a significantly greater degree with Scorpio. Both, and something else which I should mention is, we're making a consumer product. It's our practice and we also want every system to give exactly the same performance to every user. People are playing multiplayer games. They all want to, all want to have a fair advantage. So unlike PCs, laptops, or even devices where there may be a significant variation, you just don't know it. You have your cell phone of a certain brand, somebody else has another one. It may operate differently under different temperature or other conditions, or just be a bit different. We strive to not have any of that, so that makes managing power all the more challenging, as well as, and also managing performance so that everyone sees the same performance. We don't have to throw any chips away, since that costs money. And so every chip is essentially married to its particular circuit board, particular variations of the power supplies in that system. That lets us tune out. One of the things that helps us achieve the goals is to tune out all of the margin that we legitimately can through things like that.
And do you have any within shader array power gating? And if so, what granularity?
There is extensive clock gating throughout the design, both in the GPU and the CPU. In terms of power gating, we're not actually in Scorpio, we actually do not do any power gating within the shader array. We do change to operate at lower frequencies when the application, in certain operating modes. If you were just playing a Blu-ray disc, for example, then we can operate at a much lower power mode and be virtually silent, which is highly desirable in that situation.
Thank you.
That's it. Thank you.
Welcome back. Did you enjoy the eerie light? I know we didn't have too much of a coverage over here, but really nice to see. Some of you may have had glasses, could see the sun looking like a new moon. So we'd like to continue with the GPU session. Next up is AMD, Mike Mantor and Ben Sanders. They will talk to us about Vega 10. I'd like to introduce Mike upstage first. Mike has been with AMD for 25 years. He's currently a corporate fellow in the RTG, Radeon Technology Group. He is the lead architect on the Radeon product line of GPUs. And Mike is here with Ben Sanders, who are going to jointly introduce Vega 10. Mike?
Thanks, Ralph. Good morning. I see we're all still here after the eclipse. Some were telling me the world was going to disappear. Anyway, I wanted to talk to you today about our new discrete GPU. And last year we introduced the Polaris family of GPUs that really serviced and were quite successful in the mid-range and low-end markets. But we really had a need for refreshing our high-end GPU market, one that could address high-end gaming, server markets, compute markets, and in our professional workstation markets. We needed to improve our performance and our performance per watt characteristics in these markets. Also in the professional workstation market, we needed to address having access to very large data sets and large computational abilities to go with it. And then finally, we needed to do an update to our SROV hardware virtualization for the compute and server markets. So Vega is the architecture that we've developed to attack these spaces and solve these problems and return Radeon to the high-end GPU market space. So introducing Vega 10, the first implementation of the Vega architecture, we've built it in 14 nanometer technology. 12.5 billion transistors. I compared that the other day to Radeon 100, which was the first chip about 17 years ago in this product line, with I think, if I remember correctly, 20 million transistors. Vega 10 is equipped with 2 stacks of HBM2 memory and SROV-based PCIe 16 lanes. Just a die photo for you. You can see some similarities to what John showed you earlier, but there's definite differences as well. So looking at some speeds and feeds associated with this GPU, comparing to our last high-end GPU, the Fiji architecture, roughly 60% increase in clock frequency is the first thing I want to point out. This is very broad scaling capability added. The next thing would be to look at that FP16 N16 scaling, where we've made some improvements there that I'm going to talk about. And then last on the bottom of the list, in the interest of time, the L2 cache has doubled in size. That really helps us deal with the larger data sets and also the higher frequencies. So let's start with the memory system and the upgrades to the memory system. It started, we had these challenges for both wanting more capacity in the server-based class systems, having reliability on the memory. And so for us, HBM2 was the logical choice. Vega 10 is the first consumer graphics part that has HBM2. It provides the necessary ECC without performance overhead. It has exceptional bandwidth per watt characteristics and low latency needed to compete in our professional graphics market space and also the servers. And to top it off, the increased speed per pin, the 2x the speed per pin, has enabled increased capacity per stack and allows us to do 16 gigabytes, up to 16 gigabytes with 2 stacks. This is really important for some of our high-density deployments. Next, with our memory subsystem, we looked at traditionally GPU memory management, and through the APIs have really dealt with surfaces, things like texture map with its MIPS being an allocation or a render target or a command buffer or a temporary buffer. In each of these cases, you would allocate a big chunk of memory to hold the whole surface, and the whole surface would be moved into local memory at one time. This can be very inefficient sometimes when you really have sparse access to the surfaces. Not only necessarily moving all the data there, but keeping it there and keeping the footprint in place. Our team studied these access patterns and what really happens with the data that's in local memory, and found that many times only about 50% of it's ever really accessed by the rendering. And so even the 2 games that I have listed up here, Witcher and Fallout 4, are just 2 examples where more than 50% of the memory that's allocated is not really ever touched. So to capitalize on these traits, we decided to add hardware in important places necessarily to manage the local memory as a last level cache. This memory system architecture can make it appear as we have more high bandwidth memory with the high bandwidth access and a low power and low latency. And we needed to make a system that was easy for developers to use. So we built this cache controller that's distributed in our chip to really provide the necessary data along with allocation characteristics to know how to manage it. The first mode of operation is an exclusive mode of operation, and what this does is present to the APIs a bigger memory segment than what's actually in the high bandwidth memory. And then the cache controller and allocation information is used to control what data actually initially gets moved to HBM cache and what data stays there. Accessibility is tracked and is part of the decision making for deciding what actually stays in the cache. So this is, for us, a revolutionary technology that's going to be really important in server and professional applications. It enables applications to play out of the box that won't even play on current hardware. And this can be realized by really paying attention to things at the page table size and populating the cache with pages of memory instead of whole surfaces. The first thing is, after you get operating, you get a nice mix of pages that are sitting in the cache that are actively being accessed, while parts of the storage that are not being accessed can be migrated out after they've been in and not accessed for some time. Next, to improve our ability to make chips at a faster rate, AMD's implemented something we call the Infinity Fabric. This replaces many of our old logic that kind of grew and collected over the years, and it's automated many parts of that creating the fabric that connects the engines or cores to memory or I/O or chip-to-chip interconnects. In Vega 10, the version that's there has both a scalable control fabric and a scalable data fabric. The control fabric provides a connection between the system management unit and control registers throughout the different pieces of IP that are on the design. And this control fabric allows the chip to be configured and set up, and it monitors and controls the operating modes and so forth. The scalable data fabric is the fabric that handles the large data and the request transactions to move data throughout the system to and from memory. It on Vega 10 over Fiji, it provided a 67% reduction in latency over the previous data fabric that was there. And the details will be in the backup for the tests that were used to test that. So now let's step on to the Vega GPU. Start out with a graphics engine. That's a powerful graphics engine, has a flexible geometry engine that has 4 next-gen geometry engines that are improved in their workload distribution and many other aspects. And then we also have 64 pixel units. We have 4 asynchronous compute engines, which I'll talk about some more on subsequent pages. But the asynchronous engines and the graphics pipeline do share the use of the unified shader system and the memory subsystems that are there to allow multiple different kind of workloads to progress at the same time. So while many things about this architecture to some of you that are really familiar with this look kind of familiar, the architectural improvements, the process technology incorporated, and the clock uplift rates that we've done over previous GPUs, I think it will become a favorite of many developers and many users. We also include the system DMA's video encode engines for H.265 and H.264, 2 separate engines, and then video decode. Inside the 3D engine, almost every subsystem has been updated, first of all, for the microarchitecture, physical design, and design changes to get 60% frequency uplift, 60 to 70% frequency uplift. But in our limit of time, I'm going to jump into one of these features for you, which is the draw stream binning rasterizer. And with the ever-increasing demand for pixels, both from high-density displays that are getting cheaper every day, virtual reality goggles requiring more and more resolution, and more complex geometry to fill the scene with more lifelike, real scenes, we looked at a way to change the scheduling of pixels in an immediate mode renderer. And with this change, we augmented our immediate mode renderer with a method to temporally and opportunistically do tiled rendering as a subset intermixed with immediate mode rendering. This gives us, it's pretty straightforward that what we look at is at the beginning of a pipeline state that's mapped to the pipeline is the pixel formats, the MSAA formats, the render target sizes, and we pick a tile size that allows a tile and all the geometry in it to remain, its destination data to remain on chip during the rendering. And then we opportunistically capture a serial sequence of primitives, and instead of traversing one primitive all the way and then the next primitive, which really moves rasterization all the way across the screen sometimes or any place in the screen, we pick a bin and we walk the triangles in depth you can think of it, or through all the triangles that sequentially intersect that bin. And by doing that, we're scheduling the pixel shading processing work in a way that all the destination references overlap. And we get an opportunity to reuse data in a way that we can only capture by really, really large caches without that. Optionally, we have a mode that can hold on to a sample until a subsequent sample comes in. If a subsequent sample overlaps a previous one and it's opaque, we can actually remove the rendering of the pixel that wouldn't contribute to the destination anyway. Spec ViewPerf 12 Energy 01 is a typical volume rendering test that's representative of applications in the seismic, oil and gas industries, and very similar to medical imaging as well. And you can see that with this data set, having PBV, or the deferred rendering mechanism and the rasterizer turned on, more than doubles the performance. Another view of the kind of bandwidth that can be saved during rendering of some common games. And then last but not least, the performance and or performance per watt advantages of our DSBR. And you can see in here there's a couple cases like Mirror's Edge where the performance per watt gains increased more than just the performance gains, or Alien versus Predator the other way around. And you can think that when we're in a power constrained arena, removing bandwidth can save power. The whole clock can go a little bit higher and you can get more performance from the higher clock. In a case that's bandwidth limited, if we remove external requests due to smarter scheduling, we can go faster or save more power if there's other bottlenecks that are at play. So we think this is the beginning of a feature that we're going to continue to employ. It should shine even better in smaller chips that have more constrained memory systems. AMD's been behind a PCIe capability called single root I/O virtualization. Vega 10 supports up to 16 guest virtual machines concurrently on the machine at one time. There is a set of hardware schedulers. So for the compute and graphics resources, they can be scheduled one guest at a time, and there's two scheduling modes, one that gives each guest a time quanta, and a second scheduling mode that says when a guest goes idle, it yields its time. Additionally, in Vega 10, we've added H.264 and H.265 virtualization with their scheduler each, and they always operate in the liquid mode that when a job's done and the machine goes idle, it goes on to the next job. So we believe that adding the hardware scheduler offloads the hypervisor from any scheduling task other than to set up and tell the machine how to split up time and memory between the different guests. And we believe this will help remove overheads in the cloud gaming and enterprise workstation solutions. Next, I wanted to talk a little bit about asynchronous compute. Vega 10 is equipped with 4 asynchronous compute engines. And when we say asynchronous compute engines, that's what we mean. I've kind of detailed out here in the picture 4 different colors of each asynchronous compute engine. Each one is equipped with the ability to source and decode commands, the ability to dispatch work groups, the ability to track and keep do all the resource allocation and track the progress of the job that's running in that engine. It can start jobs independently of other parts. It can complete jobs independently of the graphics part or other ACE engines. Truly asynchronous in that fashion. Each one of those engines can have 8 scheduled accelerator threads. Those threads on that engine are serially scheduled on the engine and can launch and consume resources in the shared shader system. And that works very much like the graphics pipe with time multiplexing effectively getting work on and in flight. And to the left, there's a hardware scheduler, the HWS. And so for our shipping implementations, for our compute workloads, that actually schedules jobs that are using user mode queuing onto the accelerator thread descriptor slots, temporarily shifting through them when there's more jobs than under one virtual machine than what there are thread slots to mount those jobs. Then there's the SROV guest scheduler above that decides at the current time what guest all those resources can work for. Next, I'll talk a little bit about our next generation compute unit. It's been completely reworked for the higher frequency and can achieve over 1.7 gigahertz operation on a regular basis. The NCU ISA has been augmented with up to 40 new instructions, which are available. Today you can download the Vega ISA documentation. It will give you the details about those. These can be accessed through the ROCm stack. Vulkan extensions have been written and released, and they will be exposed through DirectX SM6 as it becomes available. These groups of instructions typically have advantage in 64-bit address calculations, hashing cryptocurrencies, and video processing. And each of them can also be used more generically than that as well. Now, very importantly, we've added rapid packed math, which doubles the rate of 16-bit operations, whether they're integer or floating point. Many computations that are necessary in graphics really don't require single precision, or in a lot of cases they don't. Things like normals or direction vectors or colors in many cases can all be lower precision. To really leverage these, we need developers to use them in their programs. Our drivers are optimizing for them where they can, but as developers really engage, I think we'll see them used more. Additionally, in machine learning and deep learning capabilities, this reduced precision is also very important. We also have added mixed mulad operations where each operand can be selected to be either a 16 or 32-bit operand. And this enables 32-bit encoding as well. And this reduced precision also has the benefit of increasing the available occupancy because we have full support for 16-bit registers, which we really can have twice the number of operands in those cases. So we set out to create a highly scalable architecture, one that could handle emergency workloads across compute, professional graphics, and enthusiast gaming. We've offered a new memory system using the high bandwidth cache for large working data sets. We've improved the computational capabilities thanks to the new rapid pack math and the overhaul of the next generation compute unit, and broad performance uplift thanks to the optimal new pixel engine, larger L2 cache, the improved geometry engines, the 14 nanometer FinFET process technology, and substantially higher clocks. Vega is a new architectural foundation for Radeon with a tremendous opportunity for even more improved performance as it matures, and our entry back into the high-end graphics and compute space. Next, I'd like to introduce Ben Sanders, my colleague, and a senior fellow at AMD, who will take you through what we're doing on the software side of our compute languages. Thanks, Ben.
Thanks, Mike. You guys hear me? Okay. So I do software at AMD. So I wanted to walk through our ROCm software stack. So ROCm is the Radeon Open Compute. And this is our foundation for HPC and machine intelligence. I'll focus on the machine intelligence today, but the stack is versatile enough that we can cover both markets with the pieces here. So we'll start on the bottom here. So on the bottom is the hardware. So this is the Vega 10 that Mike's been talking about. There's a couple other pieces of hardware that we support as well. On top of that is what we call the ROCm platform. So the ROCm platform is the kernel driver, the low-level system runtime that provides some basic memory management and queue facilities. That gives us a foundation that we can build languages on top of. And there's 4 main languages that we support. HCC is a forward-looking C++ development environment for people that want to do everything, the runtime and their kernels in full C++. HIP is a language that's designed to allow porting of CUDA code. So we can take CUDA applications and port them so they run on top of the ROCm platform. OpenCL is OpenCL. So that's been around for a while. It's a Chronos standard. That really appeals to people that want maximum portability. You can write an OpenCL program, run that on any GPU, a variety of CPUs, FPGAs as well, other devices. And then we have a Python solution as well. So you can program an accelerated application in Python, including the GPU kernels. So that gives us a language foundation. On top of that, there are a set of core libraries that are really important for this market. So MIOpen I'll talk about, and I have a slide on MIOpen. But that's our accelerated library for the machine intelligence market. BLAS, FFT, and RNG, those are also table stakes for HPC or for machine intelligence. So BLAS is the math library, FFT is an FFT library, and the random number generation. Those are written by internal AMD engineers with a deep knowledge and a deep understanding of AMD hardware, who deliver the maximum performance through those standard library interfaces. Nickel is an open source collective library designed for efficient multi-GPU communication. Eigen is a C++ template library that's used in a lot of these machine learning frameworks. And there's other libraries that we support as well. So with that library foundation, we can then start to port the applications that people in the machine intelligence community are familiar with. So Caffe is a primary one. That's where we've spent a lot of our initial focus, and we have a version of Caffe that is accelerated on top of the ROCm platform that's available publicly. That supports MIOpen for GPU acceleration, and it also supports multi-GPU. TensorFlow and Keras and the rest of them that are listed here, these are under various stages of internal development. A lot of interest in TensorFlow and Keras. I'll actually give an update on that. I have a slide on TensorFlow and our status there, which I'll share just before I leave the stage here. A couple points I wanted to make. So actually, AMD was here a few years ago. We talked about HSA. We actually gave a whole tutorial on HSA. HSA is still part of our solution, but it's no longer the thing that we talk about. So rather than appeal to a very small number of language developers, now we're talking about a rich software ecosystem that's really going to touch a lot more end users out there. We use LLVM as our compiler technology. And in fact, one of the things we do that's unique is we directly generate the ISA from LLVM. So we don't go through an intermediate language like HSAIL or PTX or Spear directly from LLVM to the ISA for our GPUs. And then finally, the whole software stack that I talked about is open source. So the frameworks are, of course, open source. Those are developed by a wide variety of different companies. But even as you get into the libraries and the runtime and the kernel driver, even our tools are available as open source components. And so that's a very popular feature. We see that as a differentiating item in how we deliver our software. Okay, I promised a slide on MI Open. Let me pick up the pace here a little bit. The lights are flashing at me. So key features on MI Open. This is a machine intelligence library. So as you'd expect, there's convolutions. We have a Winograd solver. It's in place, so it doesn't actually use any additional memory. The gem, the pooling, the softmax, those are the core features that people expect in a machine intelligence library. The software architecture for MI Open, the interfaces that the applications use, we support OpenCL and we support HIP, which is our CUDA porting solution. The kernels below that level were actually developed by some of AMD's best software ninjas, the people that really understand the software, really understand the hardware and how to get the best performance out of it. Some of those kernels are actually written in assembly language directly. Some of them are written in a higher level source language. The tools that our developers use, the assembler, those are available publicly so that people outside of AMD can use the same tools that our experienced software developers use internally as well. To tie this back to Vega 10, so there are a number of features we use from Vega 10. The packed FP16 that Mike just mentioned, that's 25, 26 teraflops of performance there. That's very useful in the library. We have a set of DPP instructions. These are cross-lane, a very efficient way for different lanes in a GPU to communicate and share information. So we use that. And then the LDS scratchpad memory. Lots and lots of bandwidth available from that, 13 terabytes per second of bandwidth, and that's very, very useful in these kernels. Okay, so a bit of performance. So a couple things here. So what we're looking at is TensorFlow, which is a very popular, perhaps the most popular machine learning framework. And this is running through the entire software stack that I just walked you through. So we've taken the TensorFlow code and the Eigen code together. That's about 500,000 lines of code. We've run that through our HIP porting toolkit so that runs on our ROCm platform. We've added MI Open acceleration into the library there. So we're seeing the whole software stack in action. This is running inside AMD's engineering labs. And then we're seeing delivered performance. So if you think back to the second or the third slide that Mike showed us today, the theoretical max of the flop uplift was 1.6. And so we're seeing that delivered through an actual application through the entire software stack. Okay, I'm way past time. This is a bit of a teaser for our presentation tomorrow. AMD's actually got one of the first presentations and one of the last presentations. And that's because we ship both high-performance GPUs and high-performance CPUs. It's possible to combine those together in a single system. So that's what this is showing here. One of the features of our EPYC processor is that it has 128 lanes of PCIe attached to it. And so you can hook up to 6 GPUs, still have room for some other stuff like networking and hard disk. And this is showing a potential system configuration there. More details on the EPYC I/O capabilities tomorrow afternoon. Okay, with that, I did want to take some questions. We have Ralph asked us to include some information on products. We don't have any time to talk about the details here, but if you have access to the PDF or the slides, you can see the products that we offer for the gaming space and the workstation space and the server space, which are based on the Vega 10 architecture. The upcoming iMac Pro is also going to use Vega 10 as well for people that may use the Mac products. So with that, I'll stop talking. We'll take some questions.
Yeah, we have just 2 minutes for questions, really, and then we have to move on. And name and affiliation.
Yeah, Bill Rash from Intel. I wanted to ask about the SRIOV and the context information for storing all the different machine states. Is that distributed in the logic, or do you have to move it, the context, into a more centralized storage and then bring it back again when you switch to a different execution state? Can you talk some more about how the transition occurs between the different virtual environments?
It's a mixture of both. So at the boundaries, there's a complete context that's stored for each guest and the memory that's associated with that guest. Throughout the GPU, there's effective containers, and they both isolate processes within a guest and from guest to guest. So you can think that it's a renamed container that takes on ownership of a guest, and then all the way through like the shader system and through the pipeline, an ID, a renamed ID is passed through, so every time you come out to make a reference to a memory system, you look up who you belong to. Whenever you do a translation, same kind of thing. Does that answer your question?
Yeah, how much time does it take to make a switch?
I would have to go look that up for you. You know, it's kind of ever-changing thing. You're saying between worlds, right? It's been optimized to be quite fast. The asynchronous compute engines are all instruction-based preemption. The graphics pipe power does switch at a coarser grain level. And so it's going to be somewhat still dependent on what's working in the graphics pipe.
Okay, thank you.
30 seconds.
Hi, Utku from Facebook. I have a question about your binning algorithms that you do. I was actually curious if AMD is going to, like, are you guys stop doing immediate mode and switch to complete binning, or
No.
what do you see as the future?
No, very much our rasterizer is still an immediate mode rasterizer with an opportunistic bin grab capability. So, you know, it's not a full-fledged binning circuit that has to have large intermediate storage to hold all the possible geometry, and it's not really a replay as well. It's a grab next sequential set of primitives and do binning across those. So it's still very much a forward render that has the capability to schedule the pixels that are going to be processed over a temporal batch more efficiently. Okay. And with that,
Thank you, Ben and Mike. Really appreciate it. Great talk.
All right, thanks,
Thank
Ralph.
you.
Thank you.
Now I'd like to introduce Jack Choquette from Nvidia. I'm very excited about this talk as well. He's going to be presenting on the new big chip, the V100, Volta 100. Jack's been with Nvidia for several generations, or he's led the SM processor design for several generations, so he's the lead architect. He's been doing CPU and system design for over 20 years. He's been working on many of the high-volume MIPS processors, and he's also worked on the Azul Vega network-attached processor. But today, Jack's going to tell us all about the NVIDIA's latest big chip, V100. Jack?
Thank you. Most of my slides are white, so this should be okay. Today I'm going to talk to you about the Volta architecture and how we designed it for programmability and performance. The Tesla V100 is the first chip with the Volta architecture in it. It is actually a very large chip with 21 billion transistors and 815 millimeters square. It has 80 SMs with over 5,000 CUDA cores and over 600 of the new tensor cores that we use for deep learning acceleration. It has HBM2 interface with 16 gigabytes of memory and 900 gigabytes per second of bandwidth. There are also 6 NVLinks with an aggregate bandwidth of 300 gigabytes per second. When you compare the speeds and feeds of a Volta V100 compared to our previous generation, you see that most things have improved by 1.5 to 2x. The deep learning acceleration features have actually improved the throughput for inferencing of 6x, and for training, the throughput improvements for speeds and feeds have improved by 12x. I'm going to talk to you about the NVLink and some of the improvements we've made to improve it in the Volta architecture. For NVLink, we added some things for programmability. We added CPU mastering, which allows the CPU and GPUs to directly access each other's memory at fine granularity and a flat address space. We allow CPUs and GPUs to communicate through atomics with natively supported by the hardware. And also there's address translation services, so the CPU and GPU can use the common address tables to support the flat address space. For bandwidth, we've improved it dramatically with 25 gigabits per second of signaling. For 6 NVLinks, that provides almost 2x the bandwidth improvement over our previous generation. We've added coherency in order for the CPU to be able to access efficiently and cache efficiently GPU memory. Also, there's various power-saving improvements, like reducing the number of active lanes for a lightly loaded link. Here's a couple examples of NVLink systems. You can see that on the left-hand side, there's a hybrid cube mesh for the GGX1 for a deep learning accelerator engine. On the right, for HPC application, you see the P9 Coral system for Summit. Next, I'm going to talk to you about the SM core. What you see here is the block diagram we've previously disclosed. In the next few slides, I'm actually going to dive into the details of the SM microarchitecture and exactly how it works. The Volta GV100SM has been redesigned for productivity and accessible performance. We have twice the schedulers and simplified the issue logic in order to make it easier for the compiler to target and to get more performance out of it. We have a large, fast L1 cache in order to make it easier to program to. We've improved the SIMT model, and we've added tensor acceleration for dramatic improvement in deep learning performance. All this, we've also improved the energy efficiency by 50% over our previous generation. If you look at the details of the SM microarchitecture, you can see it's actually composed of 4 completely independent subcores, each operating at 1 warp instruction per clock. A warp is considered 32 threads in the SM architecture. It has a shared L1 alley cache, and it also shares an MIO unit. MIO unit is where we do our texture, load L1 cache, and shared memory accesses. If you dive into the details of the SM subcore itself, there's a warp scheduler at 1 warp instruction per clock. It has a dedicated L0 iCache and a dedicated branch unit. It issues an instruction to a math dispatch unit that can dispatch instructions at 1 warp instruction per clock, and it can keep up to 2 or more data paths busy, depending on the instruction mix of the program that it's running. MIO instructions are sent to an MIO instruction queue, where they're sent to the MIO scheduler for later scheduling. Finally, there are 2 4x4 tensor cores, 4x4x4 tensor cores that we use to accelerate deep learning specifically. If you look at the details of the L1 and shared memory unit, you can see, as I said before, that the 4 subcores send instructions to the MIO scheduler, and the MIO scheduler will then schedule those instructions onto the MIO execution unit. It has an L1 data cache that's 128 kilobytes of storage that provides 128 bytes per clock of bandwidth. Each subcore has a 64 bytes per clock interface to the MIO unit itself. Now, the cache itself is designed to stream data very well, to get data into and stream data in very fast and very efficiently. It supports unlimited cache misses, and yet still also has a low cache hit latency. It has 4x the bandwidth and 4x the capacity of our previous generation. Now, shared memory is actually merged with the L1 cache unit itself. The storage is actually unified. So the 128 kilobytes of storage can be all cache, or you can dynamically allocate for shared memory up to 96 kilobytes of storage. So now that we have a combined L1 cache and shared memory unit, and the L1 cache and shared memory actually have equivalent latencies and equivalent bandwidth, when would you use cache memory versus when would you use shared memory, and what are the benefits of each one? To try to get the feel for the benefits of shared memory, we took some programs that were compiled and run for shared memory and remapped the shared memory to global memory and just ran it out of global memory instead. When we did this on our previous architecture, Pascal, performance on average reduced by 30%. Some things didn't slow down as much, some things reduced a lot more. When we did the exact same thing on our Volta architecture with the shared memory and L1 cache with very equivalent performance, the performance difference between using shared memory versus global memory was only 7%. So as a programmer, when would you use cache memory and when would you use shared memory? Well, for cache memory, it's easier to use. For shared memory, you have to allocate it and you have to manage the data pulling in and out. If you use the cache, the hardware will pull in your data set for you and manage it in the cache for you, making it much easier to use. And to first order, it's 90% as good. When do you use shared memory versus the cache? Well, many applications benefit much more greatly from shared memory, and you want to get that extra performance, you can actually do so. Shared memory has faster atomics, it has more banks for better bank conflict avoidance, and it's also much more predictable. For shared memory, when you access it, you know exactly what the latency is going to be. Data is always guaranteed to be there. When you're actually running out of cache, then you can, when you're hitting the cache, memory latency is good. But if you miss, you have very long missed latency, and you can stall instruction scheduling for quite a while. Next, I'm going to talk to you about the independent thread scheduling feature that we've added to the Volta architecture. The independent thread scheduling unit can be thought of as the individual thread is actually allocated and has their own program counter and has their own call return stack. Each thread is independently scheduled and can all have a guarantee of forward progress. Now the hardware does have a convergence optimizer that encourages threads to run together to be able to run on the hardware more efficiently, but it is actually not required that the threads run together. In the next few slides, I'm going to try to explain to you why we took this design approach and why we think there's a lot of benefit to this design approach. And I'm going to explain it to you first by analogy. I'll first describe how load stores are done in various architectures and compare and contrast that with how you can do program counters as well. So taking how load stores are done on a simple vector architecture, these simple vector architecture requires that the different execution lanes of the vector unit be converged, that they have to be like a base address and plus a fixed offset from that base address for each thread lane. And the hardware requires this convergence and this alignment to be part of what is being told to execute. Now, because the hardware needs to be told about this convergent alignment, the compiler compiling to this hardware must prove that convergence and must be able to demonstrate that the alignment requirements and the offset requirements for each execution lane is actually maintained and provided. Now, when a compiler compiles things, there are things like auto-vectorizing compilers that will attempt to determine from normal code that vectorization can occur. But often, in order to get the best performance and in order to get the most out of your program, programs must be written with annotations to indicate to the compiler when vectorization is allowed and when alignment and opportunities there are. Now let's contrast that with the innovation done with Nvidia GPUs. Now this is not just the Volta GPU, but this is Tesla, Fermi, Maxwell, Pascal, since the inception of the GPU. We took a different approach with load store addresses. For load store addresses and load store accesses, every thread lane has an independent address. There's no requirement that they be aligned. There's no requirement that they be converged. Now, if they happen to be converged, if they happen to be, for example, all acts in the same cache line, the underlying hardware will perform better, but it is only a performance enhancement. It is not a functional requirement. Now, from the compiler perspective, that means that convergence is only a perf optimization. It is not a functional requirement. They don't have to actually functionally guarantee it. If the compiler is aware of it and can optimize for it, that's great. If the compiler is not able to figure it out, no problem. The hardware will actually execute any code. If it happens to diverge, it is slightly slower. And this also means that programs can be written as normal. You don't have to worry. The programmer itself does not actually have to worry about trying to maintain and program the convergence. Now, the programmer can program to the underlying hardware, make sure things are converged, but if the programmer is not able to determine the convergence of load strategies, or if for a short period of time they actually want the loads and stores for the individual threads to diverge, then they will execute functionally properly on the underlying hardware, just a little slower. Now let's compare this with control addresses and program counters. If you look at scalar and predicated vector architectures or pre-Volta GPUs, the underlying hardware actually requires that convergence be prescribed. That you must tell the underlying hardware which threads are running together, when they diverge, and when they reconverge. The hardware itself must be told all the time what the PC is and which threads are actually associated with that PC. Now, because of this, the compiler must actually prove that convergence and must maintain that convergence. It must tell the underlying hardware the divergence. It must tell the underlying hardware when things converge. And not only does it have to tell the hardware when things converge, it actually must enforce the conversion. Say these threads must come together at this point. Now, threads coming together at a convergence point is essentially a form of synchronization. And when threads are synchronizing, and by the compiler forcing the synchronization, anyone writing a program to the underlying hardware must be aware of the synchronization when they're doing their own synchronization coding. If they do synchronization that is not compatible with the underlying hardware and compiler enforced synchronization, then you can get deadlock. And quite often what happens is that programmers will just write their program without synchronization in order to avoid this problem. Now we get to the Volta innovation. As I said before, each thread is running independently. Each thread is guaranteed for progress. They all have their independent scheduling. Now, if they are converged, underlying hardware can run faster and more efficiently, but it's only an optimization. Now, from the compiler perspective, convergence is also just a, actually, these are my older slides, but that's all right. Let's finish that. Convergence is just a performance optimization. That the compiler itself it may actually try to encourage convergence. It may actually tell the underlying hardware that convergence is a possibility, but that doesn't matter. As long as the program is correct, it will actually run functionally correct. This also means that program itself can be written as normal. You don't have to worry about binding synchronization. You don't have to worry about when threads converge, when they don't converge. The program itself may actually try to program to the underlying convergence to make sure it runs efficiently in the hardware. But if the programmer doesn't know what the convergence is because it's calling a library that's doing its own synchronization and doesn't really know what's going on in that library, the hardware itself will perform functionally correct, even in the presence of that unknown synchronization and convergence. Now, I want to impress upon you that NVIDIA GPUs are SIMT machines. They've always been SIMT machines, and which essentially means scalar threads on SIMD units. They have C, C++, and Fortran the way you program the machine is a C, C++, and Fortran. You program it to an array of scalar threads. Now, what happens is that a scalar compiler, will then compile it down to a scalar ISA. And it will use 50+ years of scalar compiler optimizations and knowledge in order to efficiently compile onto that scalar ISA. There's a thread virtualization technology which maps these efficiently onto a SIMD units. And the SIMD units is where the efficiency comes from. This is where our power and area and performance efficiency comes from running on these SIMD units. Now, there's a 30+ year history of SIMT where we take scalar instructions and map them onto SIMD units. And if you think about it, what the thread virtualization technology is saying is it's taking thread-level parallelism and converting it into instruction-level parallelism to run on the SIMD units. And what Volta does is actually expand the thread-level parallelism exploitation that we can do. More programs can actually take advantage of thread-level exploitation mapping onto the instruction-level parallelism. And also, it also opens up a host of compiler optimizations and additional optimizations in order to improve performance even more. So I've been talking a lot about how in the Volta architecture, threads are threads, they're independent, and they're just running independently. But very often, it's important that threads cooperate, because when they cooperate, they can actually do much more efficiently than running completely independent. And for the Volta architecture, cooperation is synchronization. So I'm going to take an example of the match.any.sync instruction. You have a warp that's running. It's a bunch of independent threads. And then they do a cooperative operation, the match.any. They synchronize, and they cooperatively perform that operation. In this example, the match.any, the instruction determines which threads have the same values. So the green threads all have the same values, the red threads all have the same values, and the blue threads all have the same values. Now, we need to inform the threads which threads they're cooperating with. So, thread 5 says, okay, I have the same values as threads 6, 12, and 23. You need to be informed that. Those results are distributed across all the warps, with all the threads in a warp, and then the threads continue operating independently again. Now, I'm going to show that we've been talking about efficiency and how efficiency is important. This graph kind of shows how synchronization, the overhead of synchronization can occur when CPU threads and GPU threads are actually synchronizing. What is happening here is that you have a mutex code where you do a mutex, do a little bit of operation, clear the mutex, get a mutex, do a little bit of operation, clear the mutex. And you do that 1 billion times in a row, so all done serially. You can do that on one thread and measure the performance, or you can take all those billions of operations that need to happen and distribute across tens of thousands of threads. and then still execute them serially. And this heat graph kind of shows you what the performance is relative to that single thread. Now, if you look at CPU threads on the y-axis, you'll see that when you get to about tens of CPU threads, it starts to get to about 10% of the performance of running things serially. If you look at the x-axis on this graph, you notice that as GPU threads, they'll get to about tens of thousands of threads before they get to 10% of the performance of a single thread. You also see that GPU threads and CPU threads can actually interact quite cleanly and well between them, and they get a pretty good distribution. It doesn't have to be just CPU threads or GPU threads. They can actually interact and synchronize quite well. Now, I'm showing the code on the right, and the code itself is the actual mutex code that's running on both the CPU threads and the GPU threads. It's just standard C++. It's your roll your own mutex. There's nothing kind of fancy about it. And this type of code, be able to run on both CPU and GPUs and have them interact, has been extremely difficult, if not impossible, on other generations of GPUs. Finally, I'm going to talk to you about the Tensor Core. And Tensor Core is an execution unit we've added to dramatically improve the deep learning throughput and performance of our GPUs. If you look at the Tensor Core, the operation of one Tensor Core, it's actually pretty straightforward. It's just a matrix multiply. It's a 4x4 matrix multiplied by another 4x4 matrix, adding into another 4x4 matrix. Now, if you look at the upper right-hand corner of the slide, you'll see that when you're doing a matrix multiply operation, you're actually doing a 4x4x4 grid of multiply add instructions. There are 32 multiply add instructions, which is incredibly dense. And the Tensor Core takes advantage of this very high density, math density of the operation in order to operate it efficiently and quickly with low area and low power. The Tensor Core is actually exposed in CUDA programming language, pretty straightforward, as a warp-wide collective operation. And the way it works is, as I'll kind of out before, for any collective operation, you have independent threads coming along. They do warp synchronizing operation where they actually execute collectively the Tensor Core operation, which then launches it off to the Tensor Core itself. Once the Tensor Cores operate and produce the results, they take the results and gets redistributed across all the threads, and the threads continue to execute as normal. The math for the Tensor Core operation is pretty straightforward. You have an FP16 input. They do a multiply and do a full precision product on it. And then they get summed into an accumulator, FP32 accumulator, and produce an FP32 result. For training, this is actually fairly important to kind of keep this extra precision in order to be able to get better convergence on deep learning algorithms. For inferencing itself, we support FP16 as well, accumulator, and FP16 result. FP16 is really all you need for many inferencing kernels. So with the new Tensor Core unit in the Volta architecture, we provide a giant leap for deep learning performance. Now, what this graph is showing here is the cuBLAS mixed precision matrix multiply operation. This is the core mathematical function that is done by deep learning algorithms. This is basically the bulk of the work that they are doing. When you compare the performance against our previous generation, the V100 with its Tensor Cores is able to perform this operation on silicon over 9 times faster than our previous generation. So I've talked to you about the Tesla V100 and the Volta architecture and the improvements that we made to it. I've talked to you about how we've improved NVLink and HBM2 memory for a fast, efficient bandwidth. I've talked to you about the new SM core redesigned for performance and programmability. I've talked about the independent thread scheduling, which enables new algorithms and new ways to exploit thread-level parallelism for increased performance. And finally, I talked about the Tensor Core, providing 120 teraflops of deep learning performance in a single chip. Now, there are many more V100 features that I just really didn't have time to get to, the 2x faster atomics, the improved int8 support, the new memory model, our copy engine page migration, MPS acceleration, and many more. All these features combine to make the Tesla V100 the fastest and most productive GPU for deep learning and HPC. Questions?
Please state your name and affiliation.
Hey, I had a question about how do you break bigger matrices into 4x4 matrix multiplications, basically? Because the numbers you showed for was 2K by 2K by 2K.
Well, if you look at a larger matrix, it can always get decomposed into smaller matrix multiply operations. And you know, a 16 by 16 matrix multiply operation can be done with 4 by 4 matrix multiplies in a grid-type fashion.
How do you, what level of memory hierarchy do you use to reduce the partial products? That was the question, basically.
We do it at all levels of the memory hierarchy. Actually, reducing the partial products themselves. I can't really go into details of a lot of the algorithms that we do and how we optimize for our kernels. In some ways, it depends on the kernel, depends a lot on the deep learning framework, what makes sense, what doesn't make sense. To first order, a lot of it is reduced all inside the SM itself, but sometimes it makes sense to reduce it across the GPU. And if you think about model-level parallelism versus data-level parallelism in models, sometimes the reduction can happen across GPUs. It really depends a lot on what the actual framework and what the deep learning network actually is.
Well, for just that problem size of 2,000 by 2,000 by 2,000 was the question, because...
Oh, what was measured? That reduction was done on the SM for what was measured, yes.
We'll have all the speakers of this session available to chit-chat over lunch outside. Thank you, Jack. Really inspiring talk. Really enjoyed it.
Thank you.